A lot of us think Python variables store values directly, kind of like a box holding an item. But what if I told you that's not really how it works at all? Today, we're going to pull back the curtain on Python variables and see how they really work with memory. And trust me, once you get this, it's going to change the way you code.
We all type something like x equals 5 and just move on without a second thought, right? But what is Python actually doing under the hood when it sees that? This isn't just some trivia question. The answer is absolutely key to writing clean, efficient, and bug-free code.
All right, so let's get right to the single most important idea here. If you've been thinking of a Python variable as a little box that holds a value, it's time to kind of rewire our brains. In Python, variables aren't containers. They're more like labels, or maybe signposts, that just point to where the actual value is living in memory.
So here's the game plan for today. We'll start with Python's big variable secret, then we'll explore where all this data actually lives in memory. After that, we'll see it all in action with some code, learn about Python's automatic cleanup crew, and then finally, we'll connect the dots and see why this is such a game changer for your programming. Okay, let's start from the very beginning and build up this new mental model the right way. The trick is to stop thinking about variables and start thinking about names and objects.
So this is the really crucial separation you have to get. On one side, you have the name, like my variable, and on the other side, you have the object. That's the actual data, like the number 100 or the string hello. The name's only job, its entire purpose, is to act as a reference, just pointing to where that object is located in memory. Okay, so we've got names and we've got objects. But where do they actually live? Well, Python organizes them into two very distinct areas of memory, what we call the stack and the heap. And understanding the difference between them is super important. Think of it like this. There's a clear division of labor. Over on the left, we have the stack. This is where all the names live. It's incredibly fast, very organized, and temporary. It's basically used to keep track of which functions are currently running. Then on the right, you have the heap. This is where the actual objects, the real data, are stored. It's a much more flexible, long-term storage area. So the stack is like a list of addresses, and the heap is the neighborhood where all the houses actually are. All right, theory's great, but let's see how this stuff actually works in practice. Seeing it with real code is where that aha moment happens. Okay, let's take a super simple line of code, x equals 10. When Python sees this, it's not just one step, it's two. First, it creates an integer object with the value 10 and finds a spot for it in the heap memory. Then, second, it creates the name x on the stack and makes that name point to the new object. So create the object, then create the pointer.
Now, what about this? Y equals x. Your first instinct might be, okay, Python's going to make another object with the value 10. But nope, it's way more efficient than that. Python just creates a new name, y, on the stack and points it to the exact same integer object that x is already pointing to. So now we've got two names pointing to the very same object.
And that right there, that's the heart of it. This is not a copy. It's a shared reference. Both x and y are just two different labels for the exact same piece of data sitting in the heap. Okay, so that was with a number. Now let's look at something a little different, a mutable type, something that can actually change after it's been created, like a list. The process starts out the same. When we say x equals 1, 2, 3, Python creates a list object on the heap and then creates the name x on the stack to point to it.
And yeah, just like with the number, when we write y equals x, we are not making a copy of that list. We are simply creating a second name, y, that points to the exact same list object on the heap. Two names, one single list.
But this is where things get really interesting. What happens if we now change the list, but we do it using the name y? When we run y.append4, we're reaching into the heap and modifying that single list object directly. Notice we haven't touched the name x at all in this line.
So, I want you to pause and really think about this for a second. We changed the list through y. The name x wasn't involved in that operation. What do you think the value of x is now? And there it is. They're both 1, 2, 3, 4. Why? Because both x and y were just pointers to the single underlying list object. A change made through one name is instantly visible through the other. And let me tell you, this is a classic source of bugs for developers who don't have this mental model down. It's not magic, you're just following the pointers.
So with all these objects popping up in the heap and names pointing all over the place, you gotta wonder, right?
what happens when we're done with them? Do they just stick around forever until we run out of memory? Luckily, no. Python has a really clever automatic system for cleaning up after itself.
The main trick Python uses is something called reference counting, and it's a really simple but honestly brilliant idea. Every single object sitting in the heap keeps a tiny little internal counter of how many names are currently pointing at it.
Let's just walk through the life of an object. We make an object, its reference count starts at 1. Then we create a second reference, maybe with y equals x, and the count bumps up to 2. Later, if we reassign x to something else, say x equals none, that name no longer points to our object, so the count drops back down to 1. And when the very last name pointing to it is removed, the count finally hits 0. The moment that happens, Python's garbage collector swoops in and poof, that memory is deallocated and made available for new objects, all automatic.
Okay, so we've been getting pretty deep into the weeds here with the stack, the heap, and reference counting. But I promise this isn't just some academic thing you can forget about. Understanding this is what separates good code from great, efficient, and truly solid code.
So here's why this actually matters to you as a developer. First off, performance. By sharing objects instead of constantly making copies, Python saves a huge amount of memory and CPU time. Your code runs leaner and faster. Second, debugging. That weird, ghostly bug where changing one thing over here mysteriously breaks something over there, you'll know exactly why it's happening. And third, scalability. This whole memory model is what allows Python to handle massive data sets and complex data structures without just falling over.
All right, let's bring it all home. It's time to officially throw out that old variables are boxes idea and lock in this new, more accurate mental model. Here are the 4 big ideas for your new mental model. First, and most important, variables are just names. They're just pointers. Second, the actual data lives separately as objects on the heap. Third, if you change a mutable object like a list, that change affects every single name pointing to it. And finally, number 4, you don't have to worry about the cleanup. Python's garbage collector has your back.
And look, if you only remember one thing from all this, let it be this. When you assign a variable or pass it to a function in Python, you're not passing a copy of the value. You are passing the directions, the reference to where that value lives in memory. Getting that one simple shift in perspective will fundamentally change how you write, read, and debug your Python code for the better.